everyone. I thank you for coming to my talk today. Today, I want to actually talk to you guys about how we can probabilistically evaluate our machine learning models. The motivation behind this technique stems from the fact that when you deploy a deep learning model in production, oftentimes you don't have the luxury of access to ground truth data. So you have to make judgments about the quality of your model's prediction using really one of the few metrics that you can extract. And often most models you can construct some sort of confidence value out of the actual model outputs. So this is actually a project that you guys can follow along. It's actually on GitHub. If you guys don't have the link, I will actually post this in the chat at the end of the talk, or Ben may post this. I will go ahead and say that a lot of the notebooks in here, they take quite a bit of time to run. So if you're trying to follow along, it's it's going to take a lot longer than what's going to be allowed in like this 30-minute talk. But just to kind of quick overview, once you download this repository, you should just be able to set it up using pipenv, which is a really nice Python environment manager, and then just open the pipenv shell and then run Jupyter Lab. So once you have yourself set up, this is about what you'll see. There's several notebooks in here. If you do want to go through this on your own after the talk, I will note that a lot of the in here, we have like these models. Those aren't actually stored in the repo themselves. So you will have to actually run through these examples yourself. So with no further ado, let's actually go ahead and get started. So if we want to evaluate a model, we first need a model. So this first notebook starts off by setting up our model. We're going to go with the very traditional cats and dogs data set just because it's real simple. So we prepare our data, we split it into, traditional train, evaluation, test, validation. Here's our beautiful cats and dogs, which they're adorable. In order to augment our data set, we do some, basic transformations. These are, I'm not going to try and spend too much time on this. This is not the main focus, but we are using just a basic transfer learning procedure where we use a pre-trained network, in this case, EfficientNet, and then add a classification head, go through, training the top layer. I do serialize out after just 2 epochs, so a partially trained version of the model. That'll come into play later. And then I continue training the classification head. Then I go into fine tuning where I do 2 epochs of fine tuning, the very low training rate. And then I serialize out this final model. And then here, just we can see just some example predictions. So here I kind of want to take a moment. So the output of your model are, in the case of a binary classification, you're actually outputting these logits, which range from negative to positive infinity. And then you actually pass that through a sigmoid function, which compresses it to 0 to 1, where the decision boundary is at the 0.5 mark. And then that you can actually convert. So I kind of, and this is arguably not the best way to do this. In fact, if you wanted, there's a whole lot of literature on probabilistic models where you actually do have like full statistical power behind here. But since we're just going with a very simple toy example in the first place, I generate a confidence by simply just taking our sigmoid values, recentering it onto 0, taking the absolute value, and then dividing it by 5. So pretty like hacky way of getting to a confidence value. But despite how hacky this value is, you actually can still use this value. It's actually more useful than you would think. So anyways, moving on, you are able to make these predictions simply just by rounding off to see whether you're closer to 0 or 1. And then using that, you can actually classify. So you're like, oh, here's cat, here's dog, here's cats, here's, oh, wait, oh, something went wrong here. Like, that's probably not a cat. I mean, I can see maybe why the model messed up. And if you look here, like, the confidence value, even our janky confidence value that we made, it's actually pretty reflects that there's some sort of problem potentially with this prediction. And you can maybe see why. I mean, the contrast is low, and even me looking at it, I kind of, it takes me a little second to come to the decision. So how do we figure out where, like, there's definitely a point. I mean, ideally, we'd want to know at what point can we like stop trusting these confidence values. And we're like, okay, we'd want a human to look at this example here and actually properly classify it. So that's where the actual probabilistic model evaluation technique comes in. So you can think about these predictions as a Bernoulli trial. So a Bernoulli trial is effectively, you can think of it as flipping a coin. But in this case, it's not necessarily a fair coin, it's a weighted coin. So you might actually, obviously as depending on how good, like, if let's say we think that we're more likely to have like a good prediction, we're going to have like a more higher chance of being correct. So in this case, oh, sorry, I just realized I just got rid of the equation. But so you can think of this as actually being a logistic function of prediction confidence. So let's just quickly jump over here. So a logistic function is kind of this S-shaped function here. And it actually can span a lot of different shapes. It could actually be inverted. It can be very steep. And there's two parameters. In this case, I'm calling them alpha and beta. Alpha simply shifts where this like slope occurs. So if we change alpha, this will simply just pan back and forth. And then beta will change the steepness of this slope. So that'll help contextualize some of these parameters we're seeing. So I think actually at this point, I'm going to go through, I think it's really good to see some sort of like fabricated data. Like if we made up some, okay, so we have this model of what it means. So we have like our alpha and beta. So the idea here is like, I'm going to have this, both of these parameters are normal distributions. This negative slope here means that it's going to go sloping upwards like we saw before. And we're going to have a logistic, which is actually makes our actual logistic function. And then it's going to actually parameterize our Bernoulli. And so in this case, with increasing confidence, the expectation here is that you're going to be more likely to be correct most of the time. So that's what we're doing here. We're generating reasonable validations here. So just as an example here, you can see if I keep running this, like sometimes I get, so 1 is correct and 0 is wrong. So I have, predictions with a confidence of 1, and I'm getting them right most of the time is what this is representing. Now then, if my confidence is around 0.5, I'm going to have, I'm going to have mistakes more often. You can kind of see that more zeros are creeping in. And then if my prediction is 0, we're going to hopefully be close to random. We're going to have like more or less like 50-50. We're like basically guessing at that point. So that's our reasonable validation simulated set here. Now we can also imagine, well, what if it's just completely random? There's absolutely no bearing on the actual result. The confidence has nothing to do with the result. So the confidence goes in, all that we do is we just take the shape. We don't care about the value. And then we just do binomial, which is actually also a coin flip, where the probability is 0.5. So it's a completely random coin flip. And so then if we look at these here, we see that now it's like pretty much just a 50-50 coin flip. And it doesn't matter if we go up or down in confidence, right? So this is kind of like our control here. Like this is bad. If this is happening, we want to know, right? We want to be able to tell that this is happening. So I generate a bunch of these like faux data sets. And actually, if you look at it just by your eye, like here's the reasonable data, and you're like, okay, I mean, like I see 1s and 0s and confidence, like and then you look at the random data, and honestly, it doesn't look that different. Like it's pretty hard just by inspection to come to some conclusion about this data. So that's where we actually want to leverage our statistical tools that we have. And so what we actually want to use is what's called a Hamiltonian Monte Carlo. But before we get there, first we need to establish this idea of a joint log probability. Now, what is this? So, so we have a prior, and these are actually something that you, as a data scientist, would select. But the values here that I'm picking are, well, I'm guessing that I'm going to be sort of centered around 0, because if my confidence is 0, I'm going to expect more or less random guessing. The scale here is just very generous. You actually want these scale values to be very large compared to where you think, so because you want it to have a very gentle effect. Because what effectively you're doing is you're saying that I want my alpha to be close to 0, like it probably is around 0, but I don't want to like be really strict. So if you want it to be less strict, you can actually just go ahead and make the scale even larger. So that's what you're doing with these prior distributions. You're saying, okay, I expect, so the negative slope, I just picked -5 arbitrarily. But what I'm saying is like, okay, well, I expect that as my confidence value goes up, I'm going to be more likely to be right. I mean, I'm hoping, you know, I'm really hoping that we have this good behavior up here, or no, that's not the good behavior. This good behavior here with the reasonable validation, not this random behavior here. But I actually still want to be able to tell. So we're going to be able to tell the difference between these two responses here. So I feed these in. I make my logistic here. So now what is coming in here? So this validation and the confidence, these are actually coming from my data. This is where I have some set of examples where I actually have ground truth. I have like actual validations. A human came in and answered yes or no, you are right to the model. And then this is the actual associated confidence that the model provided for those predictions. And then these are potential hypotheses. So you can imagine, like, let's go back, look at our logistic function. Like this line can go all over the place. It could go up, it could be going down, it could be really steep, it could be wiggling all over the place, you can imagine. But how well does a given line explain the data? So that's what we're trying to measure here. So what we do is we actually have our priors here. So this is where these priors come into play, which is we have our proposed alpha and beta, but now we want to kind of constrain them because we have, you know, some expert knowledge. We're like, okay, we expect confidence to go up. So, you know, I kind of want to encourage that behavior, not too much. The scale is insanely large, but you know, I just want to give a light encouragement to have the kind of behavior that I would expect. That this is just to help the actual search within this probability space. Then I'm going to take the actual real examples that I have, and I have some expectation of what those should be. So remember, I guess one thing to like keep in mind is that these are vectors. So this is a vector of examples, and this is a vector of the confidence associated with those examples. So we actually fed these confidences into these probabilities. We made a bunch of expectations. We have a bunch of expected coin flips. And so based off of that, how likely was that validation answer? And so since these are logarithmic, we can actually sum these up, and that's equivalent to multiplying them all together. Okay, so now we have some sort of sense of how likely a given explanation is for this data. So now this is the actual Hamiltonian Monte Carlo process. So once again, you actually, this is where the actual training, where the actual concrete examples come in. So we would initialize these with our data. We can choose the number of steps we want. We have leapfrog steps, which is actually a really interesting, I have a link at the bottom of some references if you want to learn more about this Hamiltonian Monte Carlo process. But we have an initial state, which actually these are just empty vectors. We have something called burn-in, where we're like moving and searching around in the space really quickly, but then we want to slow down and settle down into a prediction. So one thing to note is note up here that the scale is different, right? So our beta is scaled to be 10 times as large as our alpha. That's actually really relevant because at Hamiltonian Monte Carlo, it's kind of, you can imagine if it's as if it's searching a circle, it's like a drunken walk around this space, and you can't make it an oval. If you make it an oval, it's gonna not work as well. So that's why we actually have this idea of these bijectors, which will actually rescale. We're rescaling beta to be 10 times the magnitude of alpha, so that even though in our Hamiltonian space we're in a uniform perfect circle, then we rescale so that now that we'd get that ellipse that we would more likely want. So that is what these bijectors are doing. Now we have received our input data. These are our input data. And we're going to create a closure over the input data. And so we're going to use our joint log probability. We're going to basically bake in those examples. And then now we're going to have these arguments. And what are the arguments? They're actually the parameters that we are trying to learn. So we initialize the parameters to nothing, to 0. And then we define the actual Monte Carlo, which this is a bit intimidating perhaps when you first look at it, but it's not too bad. So you start from the inside and go out. So we're going to make our Monte Carlo. We have our actual probability function. We how many steps we want to take, or these are the leapfrog steps, which is helps with estimating the actual next positions. What are step sizes? Then we want to make our adaptation, like these adaptation steps are slowly decreasing how much we're moving around in that Hamiltonian space. So first, when we first start, we're like jumping around really large, and then we're sort of like, you can think of it sort of like the simulated annealing analogy, where you're slowly cooling down and you fall into some sort of very nice high probability area of this space. Because what's actually happening is every time we take a step, you make a movement, and you're actually trying to, it's a proposal to see if this is actually real. So that's kind of the analogy. We're slowly searching this space. And then this is the actual sample step. So, and at the end, we actually get a tensor of posterior alphas and posterior betas. So that is what we're actually going to be looking at. So I'll come back to these the stats function later. So first, let's just go ahead and see. Let's take our fake data, because before we even look at like actual real models, we want to just make sure that like our baseline gut checks are true. So we're going to read in our fake data where we made these like synthetic validation data, and just see what we actually get. So we're going to make our read in our validations. We make confidence, and then we have validations, which are just turning these series columns into tensors. We feed that into the Monte Carlo. We give it the validation, we give it the confidence, and then we get back these alpha and beta results. Now, what do those look like? These are actually distributions. So what we get is actually the result of having explored the space. You can see kind of a sort of Gaussian-ish looking distribution where we have, okay, so we have our beta parameter, and it's kind of searching around, and you can see that it seems to have like a mean around -3, but at the extent it can be as much as -4 to -2, but actually, like for the most part, it is negative, which means that our slope, our initial assumption is it is actually, if you remember, it is actually finding this parameter. It's actually, remember, we parameterize this to be around -3, and it actually recovered that out of just exploring the probability space. So that is good. We actually managed to find, this is kind of a trivial example. We used like basically the same model that we are testing against to generate these results. But that's like a good thing to find, that the method is actually working. Similarly, we see that we have our alpha here, and it's close to 0, which actually also matches close to where we actually had set our value here. So Gut check is good. So now here we are feeding into these HMC stats. Now this function is kind of a bear. I'm running out of time, so I don't think I'm gonna be able to cover it as much, but it is calculating effectively the mean line. So this mean line here is the average of every single one of those sigmoids that could have been one of the hypotheses. So when you're actually doing the Hamiltonian Monte Carlo, each one of those predictions, those prediction steps, it's like a line gets drawn here and it's like wiggling all around, and whether that as it wiggles around, if it's accepted as like the next potential state in the Monte Carlo chain, it's based off of if it's highly likely based off of our results. So now this this area here, this is actually the sample of our entire Monte Carlo chain. And we, I guess we can take a quick peek in the stats. We're actually taking a quantile where, so we're getting at 95% confidence interval. So these are, within this area lies 95% of all the predictions that were made during the Monte Carlo process. So this looks, very good. So let's look at the random data, because like that was like that. If there's a good result that comes out of this, there's a problem. So we read in our random data, we do the Monte Carlo, we get the stats, and we plot it, and boom, look at that. It immediately, you can see this is looking pretty fishy. You can see, okay, well, clearly with increasing confidence, there's not an increase in the probability of our answer being correct, which is good. If I saw this, I'd be like, oh my God, there's something wrong with this metric. And that's exactly what we want to see, given that we literally fed in garbage random data. Is very immediately obvious that there's some sort of problem. So this is the kind of thing that we want to see. So now let's go into, more of our quote unquote real world example with our cats and dogs model. So, here, this first example, taking our partially trained after just 2 epochs. So shouldn't have very good performance. We have our data, we read it in, we do the Monte Carlo, and this is actually what we get. It's surprisingly very good performance, which it's kind of cheating because, this was done with a transfer learning method, which was trained on ImageNet. It's a fantastic feature extractor. So not surprising that you have this really good result, but let's think about how we would actually use this in practice. Now, let's say for whatever reason, it's very important that we identify cats and dogs at a very high quantity. And well, it's like you want to look at millions of these, right? And like you don't have that many examples. You don't have that. You can maybe like send a few examples to some humans, but like their time is valuable. You don't want to waste their time looking at like easy pictures of cats and dogs. You want to give them the like hard pictures of cats and dogs that the model doesn't know. Well, at what point does the model know? Well, let's look at this. How do we interpret this? What I see here is up until like 0.5 confidence, like we have incredible accuracy, and it's only like, and you can see here, like if we, let's say our, the business need for whatever process we're doing, we're like, okay, we can have 20% error rate in our identification. Or maybe it's more strict, but you can actually set this bar right here. So you can be like, okay, well, here we have a upper bound here of how, or sorry, you don't want to look at the upper bound. You want to look at the lower bound here. And you can see like how strict you have to be to actually reach. So if we want to have 80%, you go like, okay, so now we can look at the lower bound of confidence, and we can actually accept even incredibly low confidence predictions. So that's actually a really cool result. And then if you're like, oh, okay, no, the business wants like 95%, is like all the way up here. So, okay, so we have to be much more strict. And now our prediction confidence is cut off right here. And so using this, we can actually make business rules so that we can actually employ these models in production. So now let's look at our fully trained model. So once again, you guys have seen all this before. We're doing the Monte Carlo, and here we go. So this is interesting. So why is this graph kind of like this is our like supposed to be a really good model? Like what is going on? Well, what's actually happening is you because the model is so confident, you actually only get incredibly, like, all the predictions in the data set that we have, they're all like 99%. So when you're that confident and that's the only thing you have in your data set, there's not a lot of information that we have in this low confidence area. That's why this band is so large. We can actually tell that we don't have a lot of information about these low confidence predictions. So that means that actually, despite this model being very good on our trained data set, as soon as we slip even just a little bit in confidence, we have to be really careful. So that's a really important thing to understand about these models, that you're like, okay, I made this awesome model, I fine-tuned it, and it works great. But like, you really have like now made it so that you can't, that confidence cutoff has been actually a lot higher. We just don't have that much information. Okay, so let's move on. So what if we just have a model with limited feedback? And just kind of just quickly, just to explain what's happening here, is we have our like model, and let's say, we trust everything that's like above 0.9 confidence, and we've been employing this model, and now we're going to send these to humans. And so then we have 65 examples, and that seems pretty small, but honestly, I'm not going to lie, sometimes you have real world cases where you actually have about that many. And you need to start actually making real decisions and executing your model and delivering results. So what do you do with this limited amount of results? Let's just see what we can actually conclude with that. So pretty bad. You can, I mean, you can definitely, it's immediately obvious that the lack of the data is really hurting us here. Like these confidence intervals are very wide. And so now you actually have it, you immediately know, okay, well, if we want like 0.9% like accuracy, we can't even guarantee that. That's the result here. You can't even promise that level of performance. You need to have more data. And this is a great sort of tool that you can show to a stakeholder and be like, look, this is what our expected results are. If we have, this much training data, given what we know, we can't, we need to collect more training data so that we can get to something that looks like this, and we can guarantee some level of performance. Yeah, so that's hopefully that made sense. Just barely made it in under the 30-minute mark. I will be spending a brief amount of time. I don't know if the link was posted in the chat, but here for everyone to look. If you want to look at these notebooks yourself, they're on my GitHub here for you to be able to peruse. And with that, I think I'm basically out of time. And so thank you very much.